All right. Thank you.
All right, hi, I'm Peter Dillinger. I work for Coverity in the analysis team. And I'm going to talk to you about hunting killer bugs, algorithmically. And go into more detail on all these things. And by the way, I love questions. I'm going to try and make this as interactive as possible. You know, if you think I'm wrong, say, hey, you're wrong, or you know, whatever. Okay, first a little bit about me, so you know who's talking up here. I got my bachelor's and master's at Georgia Tech, and I started a Ph.D. there, working in various areas listed there. And I went with my advisor to Northeastern University in Boston, where I finished my Ph.D. And my dissertation is on some data structures and verification algorithms. You may have heard of the spin model checker. I made some contributions to that. You may have heard of a data structure called a Bloom filter. If you look at the Wikipedia page for that, my name is on there. I did some work with the ACL2 theorem proving system. This won actually both of these won a software system award from the ACM, which was pretty cool that I got to work on both of these. And thanks to some of this work, I have an Erdish number of 3. So I've been an engineer at Coverity for about 5 years. Started down in San Francisco, and then when they opened a Seattle office, I was like, yeah, I want to be in Seattle. And I work primarily on Java static analysis, though I've also worked heavily on the C# analysis and on the C++ analysis and a dynamic analyzer for Java. And we'll get more into the details of what I mean by that. So about Coverity, it was founded in 2004 by a group of students and a professor at Stanford. We currently have more than 300 employees, so it's not a tiny operation. I'm just a small cog in a big wheel, whatever. So mostly in San Francisco and Calgary. We actually have a very rapidly growing Calgary office with some really strong talent up there. We have 11 engineers in our Seattle office. That office was started by Eric Lippert, a former Microsoftie who has a pretty popular blog about C# and coding in general. You may have heard of them. And Coverity was acquired by Synopsys earlier this year. I was traveling in India and I got this email, hey, we've been acquired. It's been a pretty smooth. Synopsys seems like a cool company to work for. So a little more about Coverity. Coverity is best known for C and C++ static analysis. So that's what made the company big as it is, and as well known as it is, at least among communities that do serious C++ development that has to behave the way it's supposed to. Think about like airplane software and software inside your TV, and people who really want software to work. A lot of those people know about Coverity for analyzing C and C++. We find bugs, and we don't waste the developers' time by showing them a lot of false bug reports that they don't care about. So we say that our false positive rate is low. Another thing that Coverity is well known for is a project called Scan. We basically offer our product for free for any open source software. So you can log on to scan.coverity.com, and if you have an open source project that you want to look at Coverity defects on that project so you can find and fix bugs, you can do that for free. It's just commercial software, we charge you money. So C and C++ kind of really built the company, but to grow and to reach a wider audience, and we've also added Java and C# static analyses. We've actually had these for a while, but originally these two products were based on analyzing bytecode, and we had kind of reached a limit in how accurate they could be and analyzing just the bytecode. So we underwent major efforts both for the Java and the C# product to make them analyze source code using the same engine as our C and C++ analysis, and we've gotten a lot out of that. It's a lot more accurate, better product. Also with Java, we've started a tool on the cloud where you can so that more people can try out the Coverity software. You can submit your code to codespotter.com and look at defects that way. Yeah, and so we have other products that I'm not going to go into much detail about, but they're cool. But you probably won't know the details, the nitty-gritty details of what I work on. Oh yeah, so has anybody heard of Synopsys, the company that acquired us? Yeah, do you know what they do? Right.
They have plenty of different franchise. They do consulting, they do product development.
Yeah, they're primarily in the hardware industry though.
Yeah.
They're like hardware validation and hardware IP and that sort of thing. And part of the Synopsys kind of sees Coverity as fitting into the Synopsys vision. There's been a major things have progressed so much in hardware development in the past 20 years, where things are very formalized and there's pretty strong, very strong verification at many levels of abstraction, and they have all this tool support to help you get things right. And a lot of people kind of see the future as, we should get software into that method of operating where there's more rigor in knowing that your thing works the way it's supposed to. And they sort of see Coverity as fitting in there. So I think that's kind of cool. Coverity static analysis is not. So I'm going to list some things that you may have heard of, and I'm going to try and convince you that we're not quite like those things, or maybe we're better. So the first one is find bugs. Who's heard of find bugs? Yeah. So find bugs is a good tool. It's an open source bug finding tool for Java. It's a good tool. It does tell you about it gives you a lot of defect reports that aren't all that compelling. It can be hard to set it up so that it finds only what you're interested in. And virtually all the defects that it finds are really shallow. It's looking for a really specific little pattern anywhere in your code. Coverity analysis is more often deeper analysis. Find bugs has like 150 different defect patterns, but they're all pretty shallow, and we don't have as many defect patterns, but they're deeper. FXCop is a similar tool for C#. Yeah, go ahead.
Does find bugs work on bytecode or source?
Yeah, it works on bytecode, so that is one limitation. For example, if you have a constant expression that you've constructed by adding some symbols together and doing some other operations, but it compiles down to a constant, find bugs only sees the resulting constant that got stuffed into the bytecode, whereas we can see where that constant originally came from, which can help us out in understanding the code. You may have heard of Lint, tool for C code, PMD, StyleCop, which is for C#. These are really like coding standards and style checkers, and we're very far from these things. These things are, they are only barely within the category of bug finding tools, in my opinion. Your compiler warnings are similar. I would encourage you to heed your compiler warnings and fix them, but they're generally shallow things that are only rarely real bugs. Your IDE warnings, similar. although these are improving, you know, IntelliJ and Eclipse have come a long way in the past 5-10 years in finding interesting bugs through warnings. But they're pretty limited. When I tried them out a month or two ago, they don't really support inter-procedural analysis, so they can't really say, this is going wrong because of something, the way the function you're calling behaves. We'll get more into that. There's some tools that that want you to, if you follow these standards and annotate your code in this way, then you can avoid these kinds of bugs. And one of the things that Coverity does is we don't ask you to change the way you're coding, you know, write your code the way that you do, and we'll analyze it that way. One more, Polyspace is another commercial product for analyzing code, but it has a reputation for taking a long time and sort of spending a long time figuring out everything it can about your program. And one of the reasons Coverity has been successful is that it's relatively fast, even on very large code bases. So our scalability is one of our big things. Yeah.
What do you mean by relatively?
A day, 2 days?
I just, earlier today I was analyzing something, and I think it took about 1 minute per 10,000 lines of code. Is that right? Yeah. And that one may have been on the upper end of how slow things can be, because there was a lot of referenced bytecode, and that makes things take longer per line of source code, because we also analyze your bytecode to some extent.
So is it fast enough? Do people include it in their normal build process?
We do have a new workflow that we're calling Fast Desktop, which gives you results very close to what you would get if you did a full analysis, but it's able to give you results very quickly for a single file at a time, or a small set of files at a time. And we have an IDE integration with that. And so you can get very close to the results you would get with a full analysis, you know, based on reusing results, previous results, and that sort of thing. You can get that quickly that way. So Coverity static analysis is also not off-the-shelf software. You're not going to like pay your $80 and then use Coverity static analysis at your desk. We really do like business-to-business deals based on how big your code base is. But we, you know, obviously I would encourage you to pursue a relationship. Anyway.
Have you considered like a per bug found business model?
I'm not, I think that's a cool idea. It might be tricky to make that work though, because you have to like say, hey, I found this bug, why don't you pay me for it? Oh wait, do I show you the bug first, and then you say, no, I'm not paying you for that? Or do I only
just
show
the
you
beginning of the description?
What?
Just the beginning of the description, the scariest part, and ...
Yeah, that might work.
Just the implications of what will happen if you don't fix this bug.
Yeah, but there is for security bugs, there is a marketplace for that. It's Secunia. I think it's one. You find a bug in a system, you put it there, and they say, hey, if you pay me, I don't make it public yet. Just do that. And if you pay, they wait for you to have a bug, a patch. So if that money goes in part to the freelance investigator, and one part for them. And then when you say, okay, I got a patch, they publish. Okay, this is a security thing, and this is the patch. So, pretty cool. If you don't pay, obviously they're gonna, you are all at risk.
So in case any of you, you want to ask?
So what does a bug mean?
We're actually going to talk about that.
All right.
Yeah, I'm actually going to solicit some of your input on that. That's coming up real soon. So in case some of your computer science course training is firing right now, so Coverity is not sound and it's not complete. So what does that mean? It's sound, it would be sound if every time it made a claim, that claim was correct. And it would be complete if every kind of bug, every bug of a specific kind is found by the tool. And you might remember from some important theorems of computer science that you can't have a tool that does both, that tells you anything interesting about a program. And so we're neither sound nor complete, and we don't try to be either one too much, and so we kind of follow this fine line where we try to make it so that the vast majority of things that we're reporting to you are legitimate things that you should be worried about. But we also try to find as many of those things as we can. And another subtle point is that even if the halting problem, you know, this problem of perfectly understanding all the behaviors of the program exactly, that's not you know, even if we could do that, that wouldn't get us everything, because what comes up more often is what was the programmer thinking when they wrote this code? And so we do a lot to look at the code and try to understand what was the programmer thinking when they wrote this, and so what can we infer will be unexpected to them, that sort of thing. So the tool is highly heuristic, if that's a term that's familiar to you. One more thing, a little bit about me. I don't know everything, far from it. So I'm not a web development expert. Probably 99% of you know more about web development than I do. So maybe that doesn't make me a super duper Java guy. But we do have a web app security team at Coverity. They know a lot more about web development than most people. One of my colleagues, Aaron Hurst, gave a talk at Java 1 on cross-site request forgery. It was really cool. I think it was supposed to be posted online, but I haven't found a link to it yet. I'm not in charge of our concurrency analysis. I know quite a bit about Java concurrency, and I can answer your questions. One of my other colleagues gave another Java 1 talk on Java concurrency. I credit myself with the title of his talk, which was How Not to Do Java Concurrency. And finally, I'm unfortunately not writing a lot of Java code these days. Our tool's written in C++ mostly, for kind of some technical and historic reasons, like we need to do some careful memory management type stuff, which you can't really do in a controlled way in Java.
How many bugs did this tool find in its own?
So that's a great question. And we do totally, you know, we call it dog fooding, you know, eating our own dog food. We have a system that we call POP, which is product on product. And so we, you know, if I make a change to the product and there's a new bug, I get an email notification saying, hey, you introduced a bug, and I can go in and look at it and say, oh, I need to fix this. Yeah, so it does definitely find some things. And we've written some custom bug finding things that are, you know, specific to APIs that we have in our own code base. And actually, we make the ability to do that is also available to customers. We have a lot of customers who write their own custom bug finding thing. So finally, an outline. So I just gave you an introduction. Next thing I'm going to do is we're going to pick on C and C++ a little bit with some spot the defect. I'm going to show you some C++ code and get you to find the defect in the code. And I'm going to show you specifically defects that would not occur in Java, just because Java arguably fixed some things. And then I want to have an interactive discussion about the question in the back. What is a bug? What makes bugs bad? That sort of thing. And then I'll talk a little bit at a high level about ways people defend against bugs and big picture. And then I'll get to show me the darn thing already, where I'll give you a product demo. And we'll kind of go through the process of looking at what the customer would see. And then I'll go into some details about our, at a medium-high level, what our algorithms look like for finding bugs, and how the system is architected a little bit. And then I'll throw in some more stuff about what you might take away from this talk. And then, time permitting, we might do a couple more defect spotting things. So, spot the defect. Here are the rules. I'm going to show you some code, and these first few are C and C++. So apologies if you don't know those very well. The rule is don't blurt out answers. Give everybody a little file to check it out. If you want to be the cool person who figured it out first, show me your hand and I'll try to ask you for an answer. So everybody got the rules? All right. Here's our first example of. Wow.
How many bugs are there?
Only one that I know of. I think we have some people who have been finding some things. So how about I go with you in the back?
Jim, CC is not initialized.
Yeah, so the variable CC is not initialized. And if we go through here, this might be false, and in which case it has to, if it's true, then it evaluates this one, and if this one's true, then it evaluates this one. And since CC was not initialized, and this is C or C++, uninitialized values could be anything. So the result of this could be anything. And it might depend on the time of day, the phase of the moon, Luckily, we don't have this problem in Java. They decided to solve this problem for us. And one thing that is kind of interesting is that it didn't jump out right away. It's a relatively simple problem, but it took some looking at to. It's not the sort of thing that necessarily jumps out at you. Here's our second example.
Does this one even compile?
Yeah, there is a comma.
You were first.
The comma is missing after the GL blend func.
Yes, so there's a missing comma there. Anybody know what that does in C and C++?
Just get nice, it appends two strings for you.
Yeah.
So the length of your array is one shorter than you expected.
Yeah, so these two strings will be combined into one string, as if you just written out one string. And the array will be shorter than this person was expecting. Java, they actually decided to fix this problem.
Well, there's the further issue, right, which is that I could be, not only is the array possibly shorter than expected, but I could be larger than 6 or 8 or whatever.
So
Depending, maybe.
I'll respond to that momentarily. Let's be sure everybody understands this. So in Java, they decided to fix this problem, and what they decided was that if you, let's see, how does it work? Basically, you have to write a plus in this case to put two strings together. Do you always have to write plus to put two strings together? Yeah. Yeah. So in Java, this wouldn't compile. Yeah.
There's a somewhat related issue which could be for people who do JavaScript with trailing commas in arrays. But certain browsers will interpret this as there's another element in the list.
But that's fine. Okay, so on the issue that you brought up, so there are some tools that would say, oh, I'm not able to prove that the value of bit is within a certain range that guarantees that once I go through this stuff, I'm accessing this array in bounds, and so I'm going to complain about that. And so Coverity analysis is generally looking for positive evidence of a defect, not I was unable to show that this can't happen. So we would not report an overrun problem. But actually, all of these examples that I'm showing you, a Coverity defect would be reported. And these are actually snippets from real open source code that we yeah.
Well, but in a larger analysis, if it found that it wasn't shown, it would report that.
Yeah, in some cases, it could, if it determined that the values were in such a range that it could cause a problem, it could possibly. Although this is probably going to confound it too much for any caller. Yeah.
So it sounds like what you're saying is it's not, like if, let's say this was a public method that I'm publishing to an API, I've clearly not done any assertions on this argument. Coverity isn't going to complain about that.
Right. We're generally looking for positive evidence of kind of a smoking gun, all the pieces you need to show that there's something wrong, or at least something inconsistent, like what was the programmer thinking?
Yeah, and it would not point you out to just put the base 2 logarithm of that bit. It will not tell you, hey man, what are you doing? Just
No.
base 2 logarithm. Do it. No?
No.
Maybe we're
Not that
drifting
smart
into
yet.
style arguments here.
Yeah.
Well, it's this static versus dynamic.
So just to be clear, it's only reporting, it only needed to look at the top code, right? It never looked at the bottom function at all for Coverity,
Yeah.
right? It's just like this pattern is probably wrong, right?
Yeah, so this is,
This could
so
be correct.
atypical.
But it's just not standard, yeah, right.
This, a human looking at this, it says, if you explain, there's, hey, if you point out, hey, there's a missing comma there, let's say, yes, that's obviously wrong.
Right.
And so that's what Coverity is trying to mimic. So here's our third one, and then we'll move on to some other stuff. Okay, I think these two guys were first, but we'll go with someone else.
I think the size of those are both questionable.
Yes.
Size of a pointer has nothing to do with the rightness of, from the perspective of left to right. And you're doing the, basically, I'm assuming this is doing the binary search, the B search thing, and it's like, your right index is totally weird, wonky after this.
Yeah, so what this code is, someone reading this code, you can infer that this one is trying to get the last index in this array. But this is actually a pointer. And when you say size of that pointer value, it gives you the size of the pointer, not the size of the thing that it's pointing to. And so we're able to detect, hey, you're trying to take the size of a pointer and then divide it by the size of each element, and that's almost never what you intended to do.
This is the type of code that we would detect this defect with unit tests. I was wondering if there were some things Coverity detects that wouldn't be detected in our standard developer testing approach.
Yeah, so that's a good point, and we're going to kind of talk about that, but I will point out that the uninitialized variable can easily go undetected.
Yeah.
What was our second example?
That was with the comma missing.
Oh, the
That
comma.
would probably get.
Yeah, that would probably be
Because
detected.
particularly if I have tests where I'm trying to make each one of those strings appear.
Yeah, although if you did naively go with code coverage, that
Yeah.
array is not likely to be considered code, and you could easily cover that function.
Even if it counted the elements, it could cover it.
Yeah. Yeah, I think we're going to touch on that some more. So, what makes a killer bug? So I want to have kind of an open discussion, and I'm over two questions. What are the kinds of bugs in Java programs specifically? Although if you want to mention other languages, that's fine. And what makes them killer bugs? And killer bugs are the ones that you're really scared of. That you're worried that you're worried that they're going to be found by the customer, not by you, and not by your QA team. And an example of a kind of bug, I'm looking for somewhat broad categories like, I didn't say null pointer exception, array index out of bounds exception, array store exception. So I just said, things that throw runtime exceptions are one kind of bug. Anybody want to throw out some other ideas?
Number format exception?
So I grouped that, well, I guess that's technically not a runtime exception, right? But
Rare, yes it is.
Rare,
Yeah.
rare and not reproducible?
so that's going to be makes them killer, rare and not reproducible.
Rare and hard to reproduce, yes.
Okay.
But only happens at the product demos.
When you plug in the printer, right?
There is a Microsoft employee here now, right?
Yeah, that'd be killer for the guys who prepared the demo.
Yeah, so
you
like,
end up here like, yes, I'm looking for a job.
so things that are kind of like runtime exceptions that aren't technically runtime exceptions, I'm gonna throw them in that same bucket. How about you?
I would say bugs that are results of interactions between systems are much harder to deal with than bugs that are just nice and occurs within a single function like the ones you were showing. Those are all, I always think those are basically pretty simple bugs, but bugs that are not produced by individual errors because assumptions are wrong between two systems that interact with each other.
Okay.
Each one can be correct, but they don't work together.
Yeah, that's a good one. And that was actually, some of my Ph.D. work was kind of in that area on model checking, where you can sort of validate that a design of interacting systems, concurrent systems behave the way you expect. The design means what you think it means.
This is so apropos for me, because I just had an argument with my boss today about which was worse. Bringing down the system, like a web service with a bug, versus what I'm really afraid of, which is a bug that produces results that pass the eyeball test but are wrong, and everything just seems to complete normally, and the users run with that until they hit the wall.
Incorrect data.
Yeah.
Yeah.
Well,
Corruption.
Actually, sorry. All the bugs are coming out, man. There's a lot of bugs out there.
Incorrect computation, maybe, or incorrect logic. How do you want to say that one?
Well, no offense.
They disagree on the contract.
I was gonna suggest corrupting data.
So, but there might be,
You may not.
corrupted is a little vague to me. Do you want to?
Yeah, I was just going to point out, so I worked at a brokerage, which didn't realize until half an hour had gone by since the trading day had already gone by, and it was a Friday, that there was something seriously wrong with their back-end systems. They're talking to the online broker, like all the clearing houses and stuff like that, and they shut down for the day, went through, fixed things over the weekend to prepare for Monday, but that half an hour cost them a shitload of money. So that was a killer bug in my I mean that's in my mind, that's an attribute for something that's killer, something that's very costly. So rocket blowing up because of the
It's like when your assets are involved,
right
not
the
your
cost.
revenues, it's your assets are involved.
But a lot of it is the deferred discovery. I had a hardware failure on a connection to the hard drive where one bit changed to 0 constantly and was not caught for days because that data that you were writing wasn't being used for like a week later. And then it was like, oh God.
The grace conditions are terrible. 2 threads, uncontrolled access. You don't get any exceptions. You just don't know what values you're going to get.
Yeah. So this is, I kind of think of that as like a
It's corrupted data.
yeah, race condition. Yeah. So that's interactions between threads where you haven't done the synchronization necessary to guarantee that your information is propagated from one thread to another.
Memory leaks.
Memory leaks. Here's I'll play the devil's advocate. Can you have memory leaks in Java?
Yes. It is a common question in interviews.
They're called memory leaks.
It is on
the
these
application
pages,
still
right?
knows it has
A
the
code that
memory.
do a memory leak. You're like,
Memory leaks that ate up all the data nodes ran for days, so that the customer says it crashed.
I would argue that the memory leak isn't necessarily a killer bug, but it's a simple workaround, which is like reboot your system once a day or every hour or 15 minutes.
well, that's costly
Well, it depends on the
because
system is.
right now, if you are paying for CPU use, the initialization you are paying like every hour, right? So it's not gonna be good, right?
Yeah.
Well, you mentioned killer bugs, so of course, I'm sure we've all read about, radiation treatment devices killing people because of bugs. But, Nimrod mentioned, rockets blowing up, and so, so if you're talking about contracts, and this is Bertrand Meyer's favorite example is the Air and Space 5, which is a really interesting case, right? Because it blew up because this thing decided to reboot because it had a sensor value out of range, and it said, well, I can't handle this, and therefore I reboot, and therefore rebooting meant I don't no longer have control of the rocket. And how would you know this is, by all means, a killer bug without killing people, but how would you even classify that? How do you know that you've got that kind of defect in your system?
That's like a requirements analysis defect. You didn't know you had that requirement?
Well, we don't want to count the whole story here, but it's like, well, but that's aerospace, right? So they have a whole system in place, and waterfall going from specs to production to control this, and yet that defect happened and cost them hundreds of millions of dollars, right?
I will say an error that is not an error unless it's put in a certain set of rules. For example, once I heard a bug of someone reading from a socket twice instead of reusing a variable, but that going again and request the value made the computer to overheat in a long run, and because of that milliseconds of extra processing, it almost killed a person.
So would that be a performance bug?
Yeah, it was in a long run, it was a performance bug that it almost cost a life.
Weird requirements?
Any other time?
Yeah.
Two things. One, I guess maybe that's okay. The one bug is when you depend on some of these features of the compiler, and those features are not complete. Like, for instance, in Java, this Java generics, which is a nightmare, is like when you put stuff on the list, it checks the type of the item. But if the type changes, and you have to remove that item from the list, it's by some less good. But that doesn't check the type. So you feel like, okay, everything passes the test of the compiler, whereas all your removes are no longer removed because it doesn't depend on the type. It has an object, for instance. So it's a case where you're using a feature that is a half-ass, half-baked concept. So it introduces bug in your code because of you depend on the compiler. Because it told you it does this and then it doesn't. So
Can I paraphrase that to say bugs that are obscured by the language artifacts? So the language makes it look like it's right.
That concept has a it's not. Well, it tells you that it's your generic aspect is done. You're inserting the wrong item in here, but it doesn't tell you on the remove.
Yeah.
Because of the contract, not the way it's written. But so that introduces the bug that you didn't expect. It's like your.
So what is the what bad can happen as a result?
Removing items from the list, like people who left are no longer there, but they're still there. So you're constantly looking at these people, and you're thinking that this guy was gone, and the rest of your logic thinks that okay, now I should insert it, but it can't be. It's still in the list.
Okay. Yeah, I think I would put that under incorrect logic, except. And I have a couple of slides on this. Your language and your APIs are supposed to help you with that.
It's similar to the
Maybe that's like a cause of the bug. You thought the compiler would prevent this kind of bug, so you didn't bother checking, and then it happens anyway.
Yeah, it does seem kind of more like a cause.
This gets me all the time. Numeric overflow.
Numeric overflow. Yeah, that's
Corrupted data.
kind of put that under incorrect logic, maybe. Did I skip you this time?
A bug that can allow you to exploit the program or even the underlying OS.
Security. So a security vulnerability?
Yeah.
Okay, yeah. Yeah, that's a
big
Latest one was the bash thing.
Yeah. Yeah.
Thanks, man.
Yeah. Like a shell shock.
Weaponized power.
Sure, how about one more from the guy in the back?
How about the fault tolerance? Let's say programmer, the assumption is that the underlying function will return, but that function never returns and the system hangs.
So,
Fault tolerance or something.
yeah, so the system hanging, that's a good kind of bug. Yeah.
I've seen something, there are no timeouts on the socket. The thread keeps waiting for the response, but the response is never there, which is not, like it comes up with the experience idea. Put a
Right.
timeout kind of, which will appear sometime in random system.
Yeah, okay. I think we have a good set here.
My favorite, the divide by zero bug that stuck a US destroyer, was it, or something like that in the late 90s, dead in the water.
Wow.
That was fixed with rebooting.
What's that? No, it literally like had a dead destroyer in the water. You guys can Google
That
it.
was a blue screen, wasn't it?
I didn't want to say it, but yes. I'm known for my opinions.
We're missing when we reach the OS limits, like too many open files.
Yes, that's a good
And
one.
on
Yeah.
code exceptions, like you have a long running program, and a code exception goes to main, and the program shuts down in the middle of the night. You will get a call at 3 a.m.
Okay, so,
Well, I wanted to talk about the killer aspect, not just those, but the, like my personal worst bug, which is kind of a combination of hard to reproduce interacting systems. So this is a linker bug, right? So back in the days, 16-bit systems, and you added a little bit more code to the program, and now a bug in the linker mislinks your code, right? So this is interacting systems, and the failure has absolutely nothing to do, right? There's no amount of the debugging about, oh, I added this code, and you can do everything you want around what is this new functionality, and yet it's, you know, it's a BIOS, right? So it's ROM, it won't even start anymore, right? And so that is my worst bug I ever experienced.
okay, yeah. I call it broken abstractions because the compiler and the linker gave you a promise, and it did not fulfill that promise.
So
Yeah.
one,
I think we need to move on.
if I may, they're related to that, there's what I would call the debugger Heisenberg bug,
Oh, yeah.
where it's broken until you start the debugger and then it runs.
The hard to reproduce.
Yeah.
Well, yes, very
No,
hard.
I think
No, it's
this-
very easy to reproduce. You just
This is
don't debug it.
I got one of the, it was concurrent, because after the debugger starts, it stops. The other thread goes on.
So,
There's no
That's
bug.
a threading.
So here are my answers. You got some that I didn't include in my answers. So runtime exception, resource exhaustion, logical error, you know, basically computing the wrong thing. Security vulnerability, data race condition, or you know, similar corruption, maybe hardware corruption. Deadlock or other hangs. Poor scalability or performance. What makes them killer? Obviously, if they're found by the customer. Hard to reproduce, hard to detect and recover from at runtime. You know, a lot of times, if there's a null pointer exception, you know, you just catch it a few things up, a few calls up, and keep going, and it's no big deal. But some of the others don't have that. Okay, so I'm going to talk a little bit high level about some of the questions that were asked. And I'll try to go quickly so I can show you some of the tool. So we've got all those different sources of bugs that we talked about, you know, computing the wrong thing, data corruption, exhaustion, and we've got these different defenses against those possible bugs reaching your customer. And none of these is perfect. You know, we start with the programmer. The programmer has to know what they're doing. Your language helps. You know, obviously some languages give you more help by being safe or, you know, disallowing certain syntactic quirks or checking for uninitialized variables, etc. And, you know, APIs can help a lot with, you know, structuring things in a way that makes sense, that don't force you to write wacky code to interact with things or to, help you develop things in a, secure from the ground up way. Obviously, you've got your compiler warnings, and these are sort of like the later you find out about them, the more costly they are. Obviously, with customers being the most costly. With all these defenses, right, it should be the case that every bug escaping development is too interesting to have been reasonably avoidable. What do you think of that? No. So here's an example for you. Who recognizes this code?
Hardly.
What?
Is it hardly?
No, it was a different one around the same time. This was it's the Apple SSL go to fail. So what happens here? So here's the first side of the if, and this is the else part.
Mm-hmm.
Yeah. So this stuff is never reached. I guess my point is that if the problem were that we have all these ways of fighting bugs, but all these interesting bugs make their way through, then that would be a different problem. But I think the problem is more like we slap ourselves on the head at most of the bugs that seem to survive. We say, oh, that should have been caught here, or oh, I recognize that pattern, or
Did anyone explain why they didn't listen to the compiler warning? Should have told them there was unreachable code here?
Why don't you ask Apple?
It seems like that tool solves it.
I have a theory which is a little later on this slide.
Okay.
That could be a feature like you want to avoid the rest of the code.
Well, that's what comments are for.
Well, how many large systems run warning checks? Very few, right? Either you run low warning checks, or you have this gigantic warning list that nobody intends to write.
So I would encourage you to read this book called The Checklist Manifesto. It's about checklists in medicine and in aviation, and
That fellow was actually just a speaker at Town Hall Seattle last night.
Cool.
Atul Gawande,
Cool. Yeah. And so he basically says, we live in such a society where things are so complicated, but we have such a knowledge base that most things that go wrong are just because people are too distracted overwhelmed by all the stuff going on, that they fail to do things that you can predict. If you have a checklist of what things you're supposed to do, like before you take off in an aircraft, or before you open up the patient.
Before you close out the patient.
What do they think the guy before him did? There's a whole chain of people who thought the guy before me did it, so he could blow it off.
Yeah, and so I kind of think of Coverity in a sense as like, we've studied all these different things that can go wrong, and we can kind of automate this checklist of checks against code.
See, when I think of the checklist manifesto and I think of automating it, I immediately think of a sequence of CI server jobs. That this job's building and running unit tests, this job's deploying, this job's running integration tests, this job's functional tests, et cetera, et cetera.
Yeah, people usually deploy our analysis as part of their continuous integration.
Okay, good.
Your language can let you down if, like us, you're kind of stuck with a crufty language that you have to deal with certain stuff from time to time. Warnings, some people only heed errors. As soon as there's one person, as soon as you cross that boundary into allowing warnings, like they just pop up magically, and it's hard to get back to no more warnings and try to keep it clean. And actually, one of the I guess one of the nice things about what Coverity offers is a platform where you can go in and, you know, like I mentioned, I get this email that says I introduced a bug into our software. If I go in and I say, oh, I think that this is, I think the tool is wrong, I mark it as a false positive, and then it remembers that, and you know, I don't have to fix anything else. So it kind of, there's a persistence there that you don't really get with compiler warnings.
But doesn't that cause us problems because you've created state into the whole situation now, and now you're not catching them, and that's the nightmare situation. It's a machine, it has to do the same thing over and over. And when you put your state, it's like, that sounds nice, but then it's nightmare.
Well, it seems to work for us. Unit tests. Unit tests are awesome when done right, but if they're a bug for bug copy of your code, then they don't do much. You know, profilers are only as, you know, only if you have realistic data. You know, I'm just kind of trying to shoot down each one of those things in your pipeline. That it's easy to cut corners, and it's easy for things to creep through. So kind of the thesis of my talk is the solution to imperfect bug defenses is to have more of them and greater variety. Because if you're neglecting this area over here, bugs are kind of going to seep through that area. And so I think of covariety analysis as just, you know, adding another layer of protection in there that kind of protects against all those different kinds of bugs that we talked about. And we have another awesome tool called Test Advisor that helps you understand your code coverage and manage it in a useful way where, you know, if you make a change that introduces code that hasn't been covered by tests, then you get notified, like a new defect report, like, hey, you added code that wasn't covered, doesn't meet what you decided was the standards for coverage. So you need to be 90% coverage on each function or something.
How does that work? Is it code coverage based, or can you take some code and say this is tested by this? Or?
Yeah, currently it's based on line coverage, and we do some filtering based on the results of our analysis that says, oh, this code can't actually be reached, so, or, you know, it's expecting, this code is only reached on some fatal condition because it immediately aborts. And so it doesn't enforce that you have to cover all that kind of code, and you can filter in some other ways. But yeah, I just wanted to mention Test Advisor because it's cool. And it kind of fits into this workflow defense against bugs. And I like to think that we also try to make the programmer smarter and more effective. You know, like I check in a bug, and also we're, you know, taking part of the development process and automating it, and so we're kind of taking a step toward that future where, you know, computers are helping you even more write software, taking on more of the development side of development work themselves. So I was talking about improving the programmer. So I introduce a bug in my code, right? I get this email, and it says, hey, you introduced a bug. And then I think, oh, yeah, I hope my friends don't see that email. I made a stupid mistake. But it's really more about, you know, being, you know, owning up to your mistakes and correcting them, and, you know, being aware that you aren't perfect. And it's more like this. Clean before check-in. She uses Coverity. Anyway, show me the darn thing already. So this, oh wait, I have a slide before this. Yes, one slide first. Typical workflow works like this. On the client side, so to speak, there's like the server side we'll talk about in a minute. The client side where you have your source code, you do this cov configure step. That really only makes sense if you're doing C and C++ where they have tons of wacky different compilers. For Java, this is just run cov configure and don't worry about what it means. Cov build is a cool piece of technology that I think is patented by Coverity, where you just say cov build and then your compile command, and it watches your compilation so that it can figure out what all your source code is. So you have your command that builds your source code. You wrap it in cov build. It watches all the compilation commands and captures what what was compiled together and what it referenced and all that sort of thing, which is really handy.
So then do you look at the libraries like the C loads also, or just the source?
Yeah, so we do actually capture reference jars and class files and analyze those to some extent, so that if you pass a pointer that might be null into a function that's only in bytecode, we can tell you, hey, this function dereferences this pointer or this reference, and so for that, things like that. We don't report defects. We don't say, hey, in this library we think there's this problem that's confined to this library. We only really analyze the bytecode for telling you about source code that's calling into it. And by the way, I have a couple of fake business cards on the table over there if you're interested. I wasn't able to get real business cards in time. So once you've done your build capture, you do your analyze, which takes the source code and referenced code that was captured and analyzes it and generates the defects. And then you commit it to a server. So typically an organization would have one or two of these servers where they where you can browse defects and look at trends and that sort of thing. And that's what we will look at now. Yes. So this is what a customer would see if they're logging into Coverity Connect. Just for fun, I downloaded something you may have heard of about a month ago called Spring Boot. And I'm not trying to pick on anybody. We find defects in lots of people's code. So by no means am I saying like, this person writes terrible code. So just keep that in mind. This code base was about 40,000 lines of code, and we found 40 issues in it, which is pretty typical. We usually find about one issue per 1,000 lines of code. Let's see. So you can see that we found a lot of resource leaks in this code. So we can look at some of them. So I am sort of picking defects somewhat at random. I did go through some of the stuff I'm going to show you just to make sure I wasn't preparing for a train wreck. But mostly I'm just picking things at random, and we're seeing what we see. Let's see, we have, we get a resource and we added, remember the input stream, copy to file. So presumably we're going to store whatever's in this input stream to the file. And in the GUI here we have a nice show details link that shows us the body of the called function. So this kind of defect is actually one that, based on my playing with Eclipse and IntelliJ recently, they would not be able to find this defect because we're creating a resource, this input stream, it's associated with a file handle, so we need to close that ourselves. We can't trust the garbage collector to take care of that in a reasonable amount of time. So we need to close it ourselves, and so when IntelliJ or Eclipse looks at this, they're like, oh, you're passing it to this copy to file function? That one might close it, I'm not sure. So I'm not gonna tell you about it. But we do interprocedural analysis, so we actually understand that called function.
Well, that's probably bad practice, isn't it, to allocate something in one scope and then pass it to another and then assume that everything's okay and not closing it?
I think the assumption is definitely a bad practice.
Well, we get, people don't seem to like tools that tell them, this is a bad practice, you shouldn't do that. But, they'd much rather be told, hey, this is really wrong.
So they're closing in the office, like here, right?
You have something?
Yeah, well, I developed for Android, and actually what you see, it's the opposite. Like, if you send an input stream to a method, even if you close it in the method, it will tell you that it might be leaked. So you have like just warnings flying around when they are not actually warnings. That kind of like is misleading because then you don't know if it's actually a leak or not. Because then you go to the method like, oh yeah, I'm closing it there, while you're telling me that I'm not closing it. So maybe it changes a little bit with the Android plugin once you have it.
Yeah, and there's kind of a belief that either my IDE takes care of it or try with resources takes care of it. But you still see a lot of code where people aren't using that, and there are cases where it just doesn't quite work right to use a try with resources statement. It's resource leaks are a very large proportion of the defects that we report, and we've invested a lot to make it work so that it can figure out, oh, is it saving away the resource in the called function or not, or is it closing it on all paths, things like that.
The GC will recover this, so it's not leaked terribly.
What?
GC will recover this, so it's not leaked terribly.
GC is not guaranteed to recover any particular object ever.
Before you run out of file handles.
Yeah, right.
So, particularly with generational garbage collection, if this gets put in a generation that is never really collected at any time in the near future,
right,
that file handle could be leaked almost indefinitely.
True.
Just because you do allocate some resource, you have to have the finally regardless, right? I mean, is there a case where just look for the finally, wouldn't that give you the same information?
So
You're going back to
the compiler doesn't require you to put a finally in.
right, I mean, like as far as you're concerned, if you don't see a finally, does that automatically raise the red flag?
No, if this function copy to file, if it had closed the input stream itself, so this is a case of kind of a confusion between the caller and the callee. What's the contract? Is the callee supposed to close the input stream? I mean, it's reading to the end. Or is the caller supposed to close it? And if the callee had closed it, we would not have reported the defect in the caller because it would have been legitimately closed without a finally in the caller.
Question. Does the tool detects as well cases where there might be a leak, not because you are not calling the close, but because maybe you are not try catching another piece of code that might crash before getting to the close, and then you will not actually close that portion of the input stream?
Yeah, so you can see here, we have some resource leaks that are just called resource leak, and some that are called resource leak on an exception path. And so, oops, I just clicked the sort thing. So the resource leak on an exception path are usually the kind of thing that you just mentioned. So let's see, here we have, random. So this function acquire returns a resource, apparently, random access file. New random access file, yes, and it returns it. Okay, I believe that. And here we have, we're doing a seek operation, and it says I'm throwing a IO exception from the call to seek and exiting that method with an uncalled exception. And so
It's before the try.
File.
It's not in.
It's before, it's not in the try, so it's not
Oh,
qualified.
yeah, exactly. So yeah, if it had been within this try, it presumably would have been closed here, but too bad.
So on your previous example, it looked like the copy file thing turned around and called another copy. You go with the input and output streams, and that didn't close because it didn't look like you could expand that.
Uh-oh, I lost my,
Does it back button?
possibly.
See, that's the real test here too,
Yeah, for a web app, does the back boot button do
You want to kill it,
anything?
open it with open Internet Explorer.
That's not fair test.
Okay, it does do something. The back
Close
button.
the out.
Sweet. There you
So
go.
it turns another, calls another copy, and yet you can't look into that other copy.
Okay, input stream.
Cool.
And it doesn't close.
It
Should be closed.
Color get closed.
So we know that read does not take this reference and stuff it away somewhere. So from that we can infer that copy doesn't.
It just seems like it ought to have shown all the way down until there was nothing else where it was passed in
Well,
to show you that it really didn't get closed.
that does work when you're talking about, so this is what we call a model link. So the callees get models, and we have specific behaviors in the callees that are called out in the model, and usually those correspond to things that happen in the called function. In this case, no escape is something that doesn't happen. And so in this function, copy to file, how do I describe to you that something didn't happen with input stream? If I, it would start to get explosive and redundant if I pointed out everywhere that input stream was used and something didn't happen. And if I want to figure out more details, I can do what I just did, which was, click on input stream, it'll highlight all the uses, and then if I want more detail about a function, I can open it up if I want to.
Or you can always look at the call stack in an IDE or something like that if you really want to get that.
Well, it showed where the error was, because the caller was the one that's bad. The caller should have closed.
We blame the caller anyway, because that's where we're reporting the defect. Let's see, dead code. missing some stuff up here. Yes. So further up in the function, there was another event which says, oh, if result class is not null, then we return from the function. Otherwise, we keep going, and then result class is checked for null again, and so this case will never be used. So this is probably a case of what I'd call defensive coding. Like, oh, well, if I reach here and it's not null, then let's do this, which is not necessarily in this case, but, you know, typically, you know, if you have code that is not serving a purpose, then maybe you misunderstood what was going on, and it's something you want to look at more closely. And, you know, a lot of times there is some legitimate, you know, runtime problem there.
Peter, do you verify that result class is local?
What do you mean?
You had some test for null, and then further on down you said, well, it's obviously not null. That's only true. That's only true if that's a local variable.
It was a local variable.
Okay.
We do. We in some cases we assume that, you know, fields aren't going to change at random. You know, if I say, you know, this dot x equals 4, if this dot x equals 4, we're going to assume that it's still 4, even though technically, you know, some other thread could have come in and changed it. We sort of assume the common case where wacky things like that aren't happening. But it means that we have to understand, if you call some other function, we have to understand, oh, might that have modified this dot x? You know, we need to worry about that.
Yeah, so what if that was a global or some vault or something? How would you distinguish between, I mean, what is the cue to say that I am going to think that it might change or not? I mean, inline versus loops or what?
I actually don't remember all the details, and maybe that's good because I'm not supposed to tell you all the picky details.
But it's also like there's a good chance that this is a bug. It could be a
Oh,
false.
it's clearly,
false.
it's
thing,
just, it's
a
dead code.
chance. So that's what we can.
Yeah, it's dead code, that's for sure.
So here's a null defect. So if this is true, then we assign name equal to null, and then here we call null function. And it says I'm resolving the virtual call to this, blah blah blah. And here I'm passing it to get logger config. Okay, and there's no link here, which probably means that this other one is defined in bytecode, and I don't have the source code to show you for it. You know, you could probably pull up the source code online in 2 seconds and verify that it does dereference it. I wouldn't say I'm 100% convinced that. So when you see virtual calls like this, you'll, you know, naturally in your head you'll want to think to yourself, are these virtual calls reasonable? You know, sometimes we get them wrong. Usually they're right. And so that's what I would have to check in this case, but it would take a lot longer than we have here to verify that those are reasonable virtual calls.
Actually, I think null is permitted.
Let's see, what time is it? Oh, it's 8:30.
15 minutes to 25 minutes. If we get one more.
Okay. Would you rather hear more talking or more like showing you defects in code?
More dancing.
More dancing. Yes. So, Gradle? You want to see Gradle? Gradle. So, yeah, I was looking around at code bases that I might analyze, and Gradle is one that we don't happen to have in our suite of, so our analysis goes through like continuous integration, and then it goes into our automated testing infrastructure where we have millions of lines of Java code that we are continuously testing our analysis against to see, what defects are we reporting, what's changed, all that kind of stuff. But Gradle is not one of them. I decided to download it, and of course it was really easy to make it work because I just did cov build. I guess Gradle itself uses Gradle, right? Gradle W, and I got my defects. Let's look at. So we have these code patterns for like things that we find. We call them checkers. So this is probably about half of the Java checkers that we have, maybe less than half. Well, certainly less than half if you count the security checkers. Let's pick some of the fun ones here. Some of the ones with like 1 or 2 defects are sometimes real fun because it found kind of a needle in a haystack. Copy paste error is a cool thing that we find. Have you guys figured out what it's trying to tell you here? Yeah, so here we have, I'm doing some stuff and I'm passing error and error. And here I'm doing some stuff that looks suspiciously similar, but I'm passing error and warning. So maybe it means, maybe I meant warning.
And you're sending ignore on top as well. So you have ignore, and then error warning, and then error.
Yeah, so I'm not 100% positive about that one, but it looks very suspicious.
So you mentioned if this is not actually a bug, what is the process to say, no, this is actually correct? How do you tell Coverity to not bug me about this one?
That's a good question. I go over here, I click false positive, I say, no, I really meant warning here, or whatever you want to type, and click apply. And then basically it goes into a dismissed status, and then it doesn't show up in most searches. If you search for outstanding defects, it doesn't show up anymore.
And that's bound somehow to that section of the code. It's going to be doing sort of a diff analysis as this lives on, and you keep editing that file. It somehow
we basically compute an identifier for this defect that involves the fully qualified name of where it is, and maybe some details about what was involved in it. And that identifier is what links it to what we call the triage. I just triaged it as a false positive, and then as long as this server is upgraded and all that stuff, it'll forever be a false positive until, unless somebody decides to change it.
So presumably if I modified that code, there must be some recognition that it's different enough that now this triage shouldn't apply, right? I mean, if I go in and edit that error again, and I now turn it into ignore, should it come up, should it not? And that's sort of
We generally err toward not showing you the defect again.
Okay.
So, there's sort of an identity associated with this, and that defect could come and go, and we still have associated with the identity of that defect that somebody said it was a false positive, so it's most likely still a false positive.
So does it integrate with any other book databases or defect tracking databases?
Yeah, but we have a team that does those sorts of integrations. Yeah.
Simple question, do you guys also have a copy paste detector?
No, I mean, we're looking for bugs, so we,
It's not, okay, style issue. All right.
yeah,
Copy paste
so.
is a bug waiting to happen.
Yeah, but I will say we have another checker that's related to copy paste error that I'm going to dig into another code base to show you one. That's where is it? It seems like a suspiciously simple pattern. You know, I don't think that that's what they meant.
Maybe they're paid by the line.
Yeah, so, you know, it looks like a suspiciously simple pattern, but, you know, some non-trivial engineering went into this checker because, you know, we figure out things like, you know, I guess I can reveal some details. You know, if there's a comment in one of these, then, you know, it indicates, you know, maybe someone was saying, I need to change this to something. I don't know what it is yet, but this one, I think this case is different, but I'm doing it this way for now, something like that. And so we won't report it in some cases like that, where there are some subtle differences or other criteria like that which go into this checker.
So, and does your tool also support like annotations or something like that where the programmer can give hints to the tool?
Yeah, to some extent, but for the most part, we just, you know, are self-reliant. Yeah, there are some specific cases where it's really helpful to add annotations, and we have some that programmers can use.
Well, I saw one of your error classes was atomicity.
Yeah.
So a lot of code is not thread safe. Like, what's your assumption about, I mean, like, which is fine if you know that this code will never be called in a multi-threaded situation. So what's the assumption of the tool? Do you have to tell it about where threading is occurring?
So we're basically clever.
You're clever.
If it looks like you're trying to write code
Okay.
that's supposed to be thread safe,
And then figure it out.
There's a synchronized
Okay.
keyword in there.
Yeah, there's a synchronize somewhere on the page. We'll check everything, right? Yeah.
Something like
yeah,
that.
Yeah, okay, that's good.
Yeah.
That's good. I like that.
and it gets you pretty far.
Yeah. That's not a bad idea.
Blogger config name is dereferenced.
Thank you.
Although the utility routine should probably be defending against that.
He's got a good point though. I mean, if you're looking at servlet code, do you understand from the context that you're going to get banged on in multiple threads?
Actually, yes.
Yeah.
Let's see if I have one of those in this. So here we have, so I call get attribute, I stuffed that into product store ID, and I'm calling session.getAttribute. Very important, that's the session. And I stuffed that in product store ID, and then later I've done some stuff to product store ID. Well, I set it to, if it was null, then I set it to something.
That can be null also.
Maybe.
It's a fallback.
And then I call set attribute. And so the problem is that the session can be shared among multiple threads serving requests, right? And so there could be if requests come in and they're running at the same time, these could interleave and you could end up with two requests following the equal null branch here. And it might not be a disaster in this case, but obviously in some other cases, it could be very bad. Yeah, and that's a case where even if you don't see synchronized all over the place, you can still, we still know from the fact that it's a servlet that they have to deal with threading concerns. Oh yes, I was going to show off this one. Okay. This is another checker that seems a little simple, but does have some engineering in it. Positions of the arguments in the call to render do not match ordering the parameters. So content is passed to page rather than to content type, and info is passed to content type rather than to info. So it's basically saying if you shuffled around some of these parameters, you would have a better fit. So it looks like it's not hard to believe that with 7 parameters, you might mix up the order. You notice that we're doing some matching of approximate matching of names here. We would have to stare at this a long time to figure out if this was a real bug, but it certainly looks
Is it all the same string type? That's one.
You're asking for trouble if you write code like that. 7 strings to a function.
Yeah.
Although this is okay, right? Content is page.
Guys are exaggerating. There's 5 strings.
Yeah, I'll quickly go through some stuff to wrap up. So how we do it, there are a few categories. We find behaviors that are unexpected. We find expected behaviors that aren't there, like with dead code. They were checking for null, but and they have this code for the null case, non-null case, and that code wasn't used. So why did they write that? Were they thinking wrong? And some subtle inconsistencies like the swapped arguments and such. I've talked about the low false positive rate. We don't want to waste the programmer's time. We lose credibility if we show them a bunch of stuff that they aren't going to care about. And we need to be reporting enough bugs also to create value. Another thing that's important to us is stable results. You can't have the results changing. If you tweak one line of code, you can't have a whole different set of results the next time you analyze. Yeah. Unfortunately, I don't think I have time to go into some of the details on how we find bugs. It's based on like control flow graphs and models for the callees and doing a search through the function with the callees, and we have some special magic that we sprinkle in here and there. Yeah, I'll skip that one. We also have some checkers that gather statistics through your whole program that says, oh, it looks like when you use this function, you're supposed to use it in this way. But in these couple of cases over here, you are using it in a different way. That is probably wrong, because 98% of the time you're doing it one way, and then this other way, time you're doing it a different way. Another thing, we have some security analysis. We can find cross-site scripting, SQL injection, cross-site request forgery, other OWASP. I think we may have covered all the OWASP top 10 bugs by now. That's a team that I'm only somewhat involved with. And they use some sophisticated global data flow analysis that's really cool. So finally, what you can learn a little bit. So one way you can think about these checkers is a lot of them are pointing out language or API problems that, don't you wish that we could fix that problem? Like, uninitialized variables, most memory resource leaks, garbage collection fixes most of your memory resource leaks. Returning a local variable, the address of a local variable of all things. That's certainly not something you can do in Java. Missing break is an interesting case. The switch statement where you have case whatever and you forgot to write break. Isn't that annoying? There happens to be a language that was invented somewhere over there that fixed that problem. Oh, this is a fun checker that I didn't get to show you. Nesting indent mismatch, where if you have something indented but it doesn't match the structure of the code, how annoying is that? And Python developers were like, hey, let's fix that. And so the indentation actually means something in Python. Stuff like that. So yeah. We do actually report a defect here. And this is the Apple go-to failed. And this case is pretty close to firing on a couple other checkers. But I think I'll close it there. Any last question?
The first one is the free, try this product for free. And the second one is?
So the second one is we'll analyze your open source software for free. And the first one is, any software, if you want to try out the tool, you can, download something that will capture your build, and then you can submit your captured build to our cloud thing that will analyze it and show you the results. Great.
On the second one, the scan open source, you can just point it to GitHub project and it'll take care of it? How do you know it's open source?
You basically say, I attest that this is open source software. And, if it's not, then people might look at it.
They put it on the way.
Most of our customers are really, they want to protect their source code very much. And, they rarely let us see their source code, we have to come begging, if they run into some sort of problem, we have to beg for their.
Kind of this little piece of source code. I thought you were going to say at that point it is open source. Just one question. Any special challenges with regards to reflection or the sort of dynamic class?
So that's one of the things that is, I would say it's more of a problem with respect to framework configurations where you have, I was looking at a problem, I was working on a checker the other day, and there was this function that looked like it just returned a field, but because of a Hibernate annotation, it could have the effect of loading the value from the database, and so someone might not, might call it for that reason. And so you can run into some weird cases if they're using,
Hibernate. Complete the statement.
Anything that uses reflection or class rewriting that does some wacky stuff. Reflection in and of itself is not all that scary because it doesn't, it's pretty rare. And when it happens, we just say, okay, I don't know what value you got out of that, and it doesn't cause much of a problem.
It only works with like plain Java, or it will work with, let's say, Java app made for Android.
Yeah, what about the Android stack? Can you
So we have,
debug the entire source for the development environment?
so we have pretty good Android support. You know, one of the code bases that we analyze on a continuous basis is the whole Android SDK. And we have some special models and things that are, you know, for Android, finding problems in Android code.
That's not open source anymore, right? SDK.
I don't know, we have some
Parts
version of it.
Parts of it. No, some version, yeah.
No, parts of it are.
Huh?
Parts of it are.
Parts.
Yeah.
Well,
The OS is not everything over it.
every year is less.
Because of your perspective.
How well does it work with custom exceptions and for features like I'm picturing also like Java 9, things that aren't yet, like the OpenJDK, things that aren't yet, you know, they're experimental. Could you get it to where maybe you want it to throw one of your custom exceptions instead of like a null pointer, or instead of like a number format exception, maybe you have a custom one if it's greater than 200. Could it do that possibly?
I don't really follow.
Oh, sorry. I was just wondering the customization ability of it.
How about
Checkers,
can you
can
create
you write
custom
your own
checkers?
checkers?
You can write your own checkers, but they don't
That's
have,
basically what I was wondering, yeah.
they don't have all the power that
Well,
we
no,
have.
because you're smarter than
No. Well, there are just some features that are, some parts of our infrastructure are kind of so complex that we don't want to help customers try and figure it out. And so we give them a somewhat, a subset that's pretty useful for them to work with.
So do you have this running on a bunch of these open source projects? Like, can I go and find out like a particular version of something or
So the way Scan works is there's someone who's in charge of a project. You know, someone requests to get a project added, and then you know someone is in charge of that project. And if you want to look at the defects for a project, you have to request permission to look at the defects. And if the person in charge of the project approves you, then you can look at their defects.
This is like open source project, like
Yeah. But you know, we find things that are potentially very dangerous and you know could be exploited. So we try to by default not share things. In fact, one of the code bases that I was showing you earlier, I was just loading up some defects and I realized, hey, there are a bunch of security defects in here that I probably shouldn't show. So let me go back and remove those security defects. We can talk about the defects that aren't likely to be security problems, but even those sometimes do.
Do you find a bug or anything with the original?
Yeah, so sometimes we, in a lot of cases, if we've, well, at least for security defects, if we find like a problem, you know, if we told everybody about every problem that we found, you know, we'd never get anything done. But for the security defects, those are, you know, higher impact, and we a lot of times inform the authors of the code.
All right, well, thank you, Peter.